Marhaba. So this will be the last session on mathematical induction, and we will introduce a variant of mathematical induction called strong induction. But okay, let me tell you what is strong induction. So remember, what was the normal mathematical induction was a technique to show that for every, say, natural number, a property of n is true. So to show for every natural number p of n is true, we need to show we show two steps. The first step is called the base case. Okay, so this is also I am telling you what is strong induction now. Okay, so to show, again, it's for the same purpose. We want to show statements about natural numbers are true, universal statements. So a statement of the form for every n, p of n. We show that the base case is true, which means the first number here is true. So p of 0 is true, that 0 has the property p. Okay, and second, again, the induction step. And here, what is the difference between strong induction and mathematical induction is with the induction step. Okay, so what is the induction step? We say for every n in the natural numbers. Remember, in the normal mathematical induction was if n has property p, then n plus 1 has property p. Okay, so this was in mathematical induction. Now, what we will do in strong induction is we will assume more information. So we will assume that not only p of n is true, we will assume that p of 0 is true and p of 1 is true, and so on up to pn. So we suppose all of this is true. So not only n has property p, but all numbers from n and backward up to the backward till we reach the initial point, all of them have property p. And this is our induction hypothesis. If all of this is true, then we show that pn plus 1 is true. Okay, so this is what strong induction is. So if you show that 0 has property p, and you show for every natural number n, if the property p holds for 0, 1, 2 up to n, then it holds for n plus 1. This means that we have shown, so from here, if these two are true, we can conclude that for all n, p of n is true. Okay, so we need to show step 1 and step 2. And the only difference is that we assume more. This is the induction hypothesis of strong induction. So let's have an example. So our example is the first part of what is called the fundamental theorem of arithmetic. Okay, theorem of arithmetic. Okay, let me tell you what is the fundamental theorem of arithmetic. It says that every positive integer greater or equal to 2 can be written as a product of primes. Okay, so where product of prime means a prime as well. Okay, so either the number is a prime or a product of primes. Okay, for example, and this product is unique up to permutation of the prime number. So let me explain what does it say. It says that start from 2, then 2 is itself a prime, and then 3 is a prime as well. 4 is not, and it is a product of primes. So 4 is 2 times 2, where both of these are primes. Now 5 is a prime, 6 is not, but it is the product of primes. It's the product of 2 times 3. And 7 is a prime, 8 is the product of 3 primes, 2 times 2 times 2. Okay, 9 is not a prime, it's the product of 2 primes, 3 times 3. 10 is the product of 2 times 5. 11 is a prime, 12 is the product of 2 times 2 times 3, right? And so on. This is what the fundamental theorem of arithmetic is telling us about the integers. In other words, it's telling us that the prime numbers are the atoms of the integers. In the same way that in chemistry, every molecule is made up from the atoms of the elements, here every integer is made up from the prime numbers. Okay? So we want to prove this statement that so this is the theorem. We want to use strong induction to prove it. And remember, what is a prime? A prime is an integer. It's a positive integer whose positive divisors are only 1 and itself. Okay, so 5 here is only divisible by 1 and 5, so it's a prime. 6 is not, because 6 is divisible by 3, and 3 is not 1 and it's not 6. Okay, so what is the theorem? That every integer n, which is bigger than or equal to 2, is a prime or the product of primes, but is the product of primes. So the product of primes include the case of being a prime. Okay, is the product of primes, or can be written as a product of primes, prime numbers. Okay, so we want to prove this. Okay, so what we did here is not a proof, it's just testing the statement. So again, to prove by induction, we need to see what is P of n, what is the property of n that we want to prove. So here, P of n, the property about the natural number, says that n can be written as product of primes, as product of prime numbers. And what we want to prove, the statement that for all n bigger than or equal to 2, P of n is true. So we want to prove this statement. Okay, that every integer bigger than or equal to 2 has the property P, which means can be written as product of primes. So we want to use strong induction. Let's use the base case. So the base case, we want to show that the first integer has the property P. So we want to show P of 2 is true. But P of 2, what's P of 2? That 2 can be written as the product of primes is true. So because 2 itself is a prime number. Okay, 2 is prime because it's only divisible by 1 and itself. So this is the base case. And now let's see what is the induction step. The induction step. So choose any arbitrary integer bigger than or equal to 2. Suppose that, so we chose n, say n is 10. Suppose that P of 2 is true. Okay, we showed it's true. And P of 3 is true. And P of 4 is true. Up to n, and P of n is true. So suppose all of this is a conjunction of n minus 1 statements. Okay, so suppose this whole thing is true. Okay, what does it mean? What are we assuming? We are assuming that 2 is a product of primes, 3 is a product of primes, 4 is a product of primes, up to n is a product of primes. And now our task is to show that Pn plus 1 is true. Again, I hope you see what is the mechanism of the induction step. You choose an arbitrary integer n, bigger than or equal to 2. And you suppose that all the integers from 2 up to n can be written as product of primes. And now we need to show that the integer, which is the successor of n, so n plus 1, is also a product of primes. So this is what we want to show. And we assume this. So this is our induction hypothesis. This is our induction hypothesis. So previously in mathematical induction, we just assume n is a product of primes. But here it's not enough. We need to assume more. Okay, so let's show that. So in other words, so we need to show that Pn plus 1 is true. This means, i.e., show that n plus 1 is a product of primes. Okay, so let's show this. There are two cases. Case 1. Okay, look at n plus 1. If n plus 1 is a prime, we are done. And if n plus 1 is a prime number, then n plus 1 is a product of primes, and we are done. If n plus 1 is a prime, then there's nothing to show. Then P n plus 1 is true. Okay. Now case 2. If n plus 1 is not prime, is not a prime number. Okay. So here we have only two cases, whether n plus 1 is a prime or not. Now what does it mean that a number is not a prime? This means that n plus 1 has a divisor which is not 1 and not n plus 1. So this means that n plus 1 can be written as the product of two integers, a times b, where both a comma b are not 1, they are strictly bigger than 1, and not n plus 1, and strictly less than n plus 1. Okay, and this means that a comma b is bigger than or equal to 2 and less than or equal to n. Okay, so look, what do you know about a and b? They are integers and they are between 2 and n, which means they are among these. They are either 2 or 3 or 4 up to n. This is what we know about a and b. They are among the integers from 2 to n. But our induction hypothesis tells us that any number between these numbers from 2 to n have the property p. So by the induction hypothesis, we know that P of A is true because A is between 2 and n, and P of B as well. Okay, what does it mean that P of A is true? This means that A can be written as product of primes, as product of primes. Okay, meaning that A is equal to P1, P2 up to Pk, where each Pi is a prime number, right? For example, A is equal to 3 times 7 times 13. Okay, this is the meaning that P of A is true, that A can be written as product of primes. Okay, again, and P of B is true. We know also P of B is true. This means that B can be written as primes, and so B is equal to, say, Q1 times Q2 and so on times, say, QL. We have L prime numbers and we multiply them together, we get B. So where each Qi is a prime. Okay, but now look what we have. We know that n plus 1, what is n plus 1? It's not, we said we are in case 2, it's not prime, and it's equal to A times B. It's equal to A times B, but A is the product of the primes Pi's. So A is P1 times P2 up to Pk. And what's B? It is the product of the primes Q1, Q2 up to Ql. So this shows that n plus 1 is the product, all of these are primes. Okay, is the product of prime numbers. So this shows that n plus 1 is the product of primes. So in the two cases, in case 1, we showed that n plus 1, p of n plus 1 is true because n plus 1 itself is a prime. And in case 2, we also showed that n plus 1 is the product of primes. So this means that we showed, so by strong induction, we proved that for every n bigger than or equal to 2, p of n is true, which means n can be written as product of primes. As product of primes. Okay. So this shows the first part of the fundamental theorem of arithmetic, that every integer bigger than 2 or equal to 2 is the product of primes. Okay, maybe you want to see another example. Look at 30. How 30 is the product of primes? It's 2 times 3 times 5. Okay, and look, each one of these is a prime number. Okay, you want to see 55, for example, it's 5 times 11. And so no matter which integer you choose, you will write it as the product of primes. And the second part of the fundamental theorem of arithmetic tells us that these numbers are unique up to arrangement, which means that you cannot find other prime numbers other than 2, 3, 5, which when you multiply them together, you get 30. So we will prove the uniqueness when we study number theory. So let's stop here. But okay, before I stop, let me revise what is strong induction. It's almost the same as mathematical induction, but in the induction step we assume more. So again, to show that the property P holds for every natural number n, say, we do two things. The base case, we show that 0 has the property P, and second, we assume that all the numbers from 0 up to n, where n is any natural number, and all of these have property P, and using this hypothesis, we show that the successor of n, which is n plus 1, has property P. And if you show step 1 and step 2, this means that every natural number n has property P.